Good morning, everyone. My name is Jiasheng Duan. Today, I'm glad to introduce our paper, Semi-supervised cross-modal hashing with graph convolutional networks. As we know, there has been an explosion of multimedia data on the Internet during the last decade, and data online exists in different modalities and are collected from various resources. For example, we see images on Instagram, we watch videos and movies on YouTube, and we post and read text messages on Twitter or Facebook. This phenomenon leads to the increasing requirements of multimedia interaction techniques, especially cross-modal retrieval. So, what is cross-modal retrieval? A typical cross-modal retrieval system takes queries from one modality to retrieve data from other modalities with similar semantic information, namely class labels. To complete this task effectively, many researchers have paid attention to hashing. Hashing is a widely studied solution to the approximate nearest neighbor search. It aims to transform a data item to a low-dimensional representation. In other words, a short code consisting of a sequence of bits, for example, 32 bits or 64 bits. We call the codes hash codes or binary codes. Hashing has low computational cost because it uses XOR operation to calculate Hamming distance between data points. In the context of cross-modal retrieval, cross-modal hashing aims to project high-dimensional data features in different modalities into a common low-dimensional discrete Hamming space. It targets to generate a set of reliable common hash codes that can represent data in all modalities. The key challenge of cross-modal hashing is how to preserve the underlying inter-modal and intra-modal correlations. Besides limited by the training datasets available, most of the existing work focuses on image and text modality. Therefore, without loss of generality, we concentrate on these two modalities in this paper, and our method is easy to expand to deal with more modalities. Until now, there has been a rich line of work for cross-modal hashing, which can be roughly separated into three categories: supervised, unsupervised, and semi-supervised hashing. Supervised hashing provides guidance information, namely class labels, to define the similarity relationships between different modalities. It usually has relevant higher accuracy because of the guidance information, but it's hard to get large-scale datasets since the data needs to be labeled by a human. Compared with supervised hashing, unsupervised hashing defines the similarity relationships across modalities based on the data distribution, and there is no class label available. It has a big advantage, which is the large amount of cheaper training data. So, to take full advantage of both supervised and unsupervised cross-modal hashing, we paid attention to semi-supervised hashing, which provides a feasible solution to benefit from both supervised information of class labels and the cheap and labeled data. Hence, we proposed a semi-supervised learning method, semi-supervised cross-modal hashing with graph convolutional networks, and we call it CMGCNH for short. Well, as we aim to design a semi-supervised method, the first problem we need to deal with is how to take full advantage of unlabeled data and transfer information between labeled and unlabeled data for two modalities. For this problem, we solve it with graph convolutional networks. We call it GCN for short. So, what is a GCN? A typical GCN consists of one or multiple convolutional layers, namely GC layers. It conducts spectral convolution operations on a given graph to integrate information from the neighbors of a node into the features of itself. Now, the operation on a GC layer has been simplified to Formula 1. The input of a GC layer is a graph and the adjacency matrices of the graph nodes, namely the relationships between the nodes. So, because a GCN integrates neighbors' information to graph nodes, for semi-supervised cross-modal hashing, it allows to transfer information between labeled and unlabeled data if they are organized into a single graph. However, it's impossible to organize all data points in one modality into a single graph, because the size will be too big. In addition, as GCN runs in a transductive way, namely the number of nodes in a graph is fixed, so we have the problem that how to integrate queries into a constructed graph. Inspired by the paper, Graph Convolutional Network Hashing, we use anchors to be the medium to solve this problem. To be specific, we first randomly select a small number of paired anchors from labeled data. Then, for a small batch of images and texts, data points, including labeled and unlabeled data, are organized into two undirected graphs with the selected anchors. So now, the nodes of two graphs are the data points and anchors, and the edges, namely the adjacency matrices of the graph nodes, represent the similarity relationships between data points and anchors. We define the edges by the rule shown in Formula 2. For the label data, if a data entity shares at least one class label with an anchor, we define their relationship to 1, otherwise it's 0. For the unlabeled data, if the anchor is in the k nearest neighbors of a data point, then their relationship is set to 1, otherwise 0. So in this way, we build the image graph Ziwei and the text graph GT, and the asymmetric adjacency matrices Z hat V and Z hat T for Ziwei and GT indicate the relationships between data entities and the modality-specific anchors. Now, the data set can be separated into mini-batches, and queries are organized into graphs in the same way as the unlabeled data. Furthermore, we also build the graphs of anchors for two modalities, respectively. The anchor adjacency matrices A hat V and A hat T are defined in the same way as the relationships between the labeled data and anchors. Now, we can build the asymmetric graph convolutional networks, which consist of a pair of asymmetric graph convolutional layers, namely GC layers, and a set of GC layers in the middle. For simplicity, here we assume the number of GC layers is only 1. As shown in Formula 3, for one GCN, we aim to learn the weights of the three layers, W1, W2, and W3. The first GC layer aggregates the features of the data points into the anchor nodes through convolution operations, according to the asymmetric adjacency matrix, and H1 is the output of this layer. Then, the middle GC layer convolves the aggregated anchors H1 with their adjacency matrix A hat and outputs H2. These two layers are followed by activation function sigma. Finally, the last GC layer calculates the low-dimension features of each data points through the weighted summation of anchors H2 and the asymmetric adjacency matrix, and is activated by the tan function. So the output H3 is the soft representation of the hash code for the data points. Now we know how the GCN work. Then let's look at the problem definition of our semi-supervised cross-modal hashing method. Given a cross-modal dataset O consisting of an image site V and a text site T. VL and TL are a small number of labeled data, while VU and TU are unlabeled data. We target to learn two sets of hash functions HV and HT for images and texts, which are able to generate reliable common hash codes B of two modalities. We built a dual-branch asymmetric graph convolutional network, CMGCNH. This is the overview of our model architecture. We can see that our model contains two modality-specific branches, and each is built with two AGC layers and a group of GC layers between them. The way of building and operating the model is the same as the AGCN we introduced just now. After we get outputs of the two branches, namely the soft representation of hash codes UV and UT, including labeled points UVL, UTL, and unlabeled points UVU and UTU. We first combine the labeled points together with hyperparameters lambda1 and lambda2, so we get the integrated representation UL. This is the cooperative learning way, in which we integrate the information of the two modalities together. Then we assign all soft representations to the discrete binary codes. After that, we put these outputs into the loss functions. Our loss function consists of three parts. Firstly, as introduced, we expect to learn two modality-specific hash functions for images and texts to produce the unified binary codes B for all. That means the generated labeled ULV and ULT should be transformed to a common B through the sign functions. Therefore, we employ the quantization loss between the continuous ULV, ULT, and the discrete BL as formula 4. We also consider the original semantic structures, namely inter- and intramodal similarity relationships, for which we strive to make the distance between the encoded objects with shared labels as close as possible, while the pairs with dissimilar labels far away from each other. Hence, for the label data, we propose to minimize the classification error from the hash codes BL as formula 5. Then, for the unlabeled points, to keep the code base uncorrelated and balanced, we add two constraints to maximize the information entropy as formula 6. Finally, we add these three parts together to calculate the total loss. To evaluate the effectiveness of our method CMGCNH, we conduct experiments on two widely used cross-modal datasets, MIR Flickr dataset and Newswhite dataset. MIR Flickr dataset consists of 25,000 images, and Newswhite contains 260,000 of images, which are both collected from Flickr. Each image of these two datasets are associated with multiple textual tags, and each of them belongs to at least one common category. MIR Flickr totally has 24 categories, while Newswhite has 10 classes. We represent images with 4,096 dimensions deep feature vectors extracted from a 19-layer VGGNet, and represent the text with back-of-word vectors. We compare CMGCNH with 2 supervised methods and 4 unsupervised methods, and evaluate them with MAP scores and precision recall curves. This is the MAP results on the two datasets. We can see that CMGCNH consistently performs the best in all methods on two tasks for both MIR Flickr dataset and Newswhite dataset. Besides, to explore the influence of the number of anchors, we implement experiments to calculate the MAP scores when this number changes from 100 to 1000 with the same model setting on 64 bits. From the left finger, we can see that the performance is getting better along with the number of anchor points increasing. This can be explained as that the more anchors used in the graph, the more information of the data nodes is preserved and propagated. It also demonstrates that the design of anchors used to keep and transfer semantic information is effective. And for exploring how the depth of GC layers affecting the model performance, we conduct an experiment to observe the changes of MLP scores when the depth rises from 1 to 10. From the results in the right finger, we can see that the score reaches the peak at 3 and then started to drop down. Hence, we suggest that the over-deep GC model will lose the information during forward propagation, while over-shallow GC network cannot fully aggregate and retrieve the node features. So we fix the depth to 3 in our experiments to achieve the best performance. Okay, in conclusion, to the best of our knowledge, this is the first attempt to utilize a GCN architecture for scalable cross-modal hashing. And in our model, the cooperative multi-model learning strategy preserves the similarity relationships of intermodalities, while the graph-based architecture within each branch preserves intramodality correlations. And experiments demonstrate that CM-GCNH can achieve superior performance than other methods. Well, that's all for my presentation. And next, I will answer some questions that you may ask. Firstly, why is the graph called asymmetric GCN? Why is it asymmetric? This is because the adjacency matrix of the graph is asymmetric. As shown in the figure, the size of matrix is n times p. N is the number of data points, and p is the number of anchors, and p is much smaller than n. The second question is when integrating the labeled codes of two branches, how to set the ratio between images and texts. In other words, what are the values of lambda 1 and lambda 2? Well, actually, we conducted an experiment to decide these two values, and since the images can provide more information than texts, the value of lambda 1 is bigger than lambda 2. So we set lambda 1 to 0.7 and lambda 2 to 0.3. The final question. In the experiments, you tested the effect of the number of anchors used in the model, but why did you only test the number from 100 to 1000? Well, actually, we tested more numbers, but after 1000, there is no significant increase, so we don't show it here. Well, this is the end of the presentation today. Thank you for your attention.